shall look at application modeling. So, considering a model relationship of an ROC circuit, ROC. In an ROC circuit, we know that charge Q is equal to CV, and voltage itself of a capacitance of a capacitor is charge divided by the capacitance. So if this is known and we have an electric circuit system of a resistance R merging with the capacitance of a capacitor, then of course we have a linkage, which is a power source. So if that is noted, for example, we could in fact make it a merge, an equality. So let's say there is a C here. Now this is the capacitance of the capacitor, and this is the power source, which is E, the electromotive force. So that is to say, V total is equal to V across the resistor plus V across the capacitor. Now this is Kirchhoff's relationship for a model of an electric circuit system. Of course, the current relationship is in this format, and it comes down to the source as a back effect. So that is to say, the voltage across here is the VR, and voltage across here is the DC. So at that level, we relate it by modeling. The mathematical model will now give you, for Kirchhoff's law, you use Ohm's law here, and Ohm's law, as it is current multiplied by resistance, plus the voltage across the resistance, which is charge divided by capacitance of the capacitor, is equal to the total voltage running the circuit, which is electromotive force. So current itself has an issue based on electrolysis and Sir Faraday's relationship. This relationship gives you resistance multiplied by dq dt, an instantaneous relationship of quantity of current flowing with respect to time, plus Q divided by C is equal to the electromotive force running the system. So dividing through by R, we'll be having dq dt plus Q over RC is equal to electromotive force over R. We can use Laplace transform model. We can also use the linear first order differential equation solvable by integrating factor technique. And that gives us Q exponential integral reciprocal RC dt is equal to integral E over R exponential integral reciprocal RC dt plus arbitrary constant C. We are going to use K so as to avoid analogy and unnecessary comparison with the capacitance of the capacitor, since it's an application problem. So take note that this really is taken from the general formula of a linear first order differential equation, which is dy dx plus py equal to q, which solution formula is y exponential integral p dx is equal to integral q exponential integral p dx differential s plus arbitrary c. Now, globally, this is the general format of a linear first order differential equation. This is the characteristic expression, and this is the solution formula. So, going by this relationship, when we have q becomes the y, and this is the y, and that is why there is q here. So that reciprocal RC becomes the p, which is the coefficient of y, and y becomes q, so that is why it is reciprocal RC. Integral of q becomes the last term here, which is E electromotive force all over the resistance of the resistor. So exponential integral reciprocal RC dt plus arbitrary k, the constant. So furthermore, to get our final solution to this challenge is to integrate completely, which gives us the charge model, which is a function of time domain, exponential t over RC when we integrate is equal to e over c integral exponential t over RC t over RC. Now multiply by dt plus arbitrary k when we integrate. So furthermore, charge function of time domain is exponential t over RC is equal to e divided by, note that this is actually r when it is coming out of the bracket, e over r dot RC over 1 exponential t over RC plus arbitrary constant k. So if arbitrary constant k exists, we simplify further to give us r cancel r, and this gives you charge is a function of time exponential t over RC is equal to e multiplied by the capacitance of the capacitor exponential t over RC plus arbitrary k. You could divide through by exponential t over RC, and finally charge is a function of time domain is equal to E multiplied by the capacitance of the capacitor exponential t over RC divided by exponential t over RC plus k over exponential t over RC. So this gives us E multiplied by capacitance of capacitor t over RC divided by, this cancels out completely, and so that we will not have this again. If they cancel out, then plus k exponential minus t over RC. That is the end of the proof, and this gives you the charge of the relationship.